Hey folks, in this video we're going to briefly talk about the energy stored in an inductor. Okay, and if you need a moment to pause the video and just copy that really easy circuit, go ahead and take that now. All right, so uh, we're going to talk about energy and power. Okay, but first I'm going to start with Kirchhoff's loop rule. So I'm going to start here. I'm going to work my way clockwise. And we know that for voltage, okay, first we hit the battery, which is just E naught, okay. Then we go through the resistor, so minus IR, and then minus L di dt equals 0. So that's our three voltages that add up to 0. Now I'm going to multiply each of those by I. So I got I E naught minus I squared R. Hopefully you're seeing some familiar terms here. Minus Li di dt equals 0. What are these terms? What do they represent? Well, this is the power input of the battery. That is the rate at which the battery is adding energy to our circuit. It would be measured in watts. It's IV. Okay. What is this? Well, that is the power output of resistor. And what is that energy turning into? It's turning into heat. Okay, so here's what we got. The battery adds energy to our circuit. We lose some of that energy due to heat in that resistor. What's this third term all about? Okay, well, it's got to be power of the inductor. Okay, now what does that mean? Right, the power of the inductor. Well, what's happening is you're storing electrical potential energy in that inductor. Imagine you were pushing a block up a ramp with friction. Uh, this first term would be you doing positive work on the block. This term would be heat loss due to friction. This term would be gravitational potential energy, the rate at which you're increasing the gravitational potential energy of the block. Well, we basically have the same thing going on here. This first term is the rate at which you're adding energy to the circuit. This is the rate at which you're losing heat out of the circuit because of the resistor. And this is the rate at which you're storing electric potential energy. Now, where is that energy being stored in the inductor? Well, remember what an inductor is. So here's, if I take this thing and I blow it up, you've got something like this. It's a bunch of wire with a current running through it, right? Well, that wire makes a magnetic field, right? Okay, we talked about this previously. As this current increases, you're increasing that magnetic field. It turns out that the energy that we store is literally stored in this magnetic field, in that space, okay? As a matter of fact, the next video, we're going to talk about the energy density per cubic centimeter of energy in that space, in that region that contains the magnetic field, okay? But for now, I just want you to know where it's being stored. So we're storing electrical energy in the magnetic field that's in the inductor that's in our circuit. All right, now, the other thing I want to know is how much total energy is stored in the inductor at a given moment. Okay, so I'm going to take, knowing that energy or work, which is going to be U of the inductor, okay, and it's technically it's negative work, but then it's positive work, so don't worry about all that. So, but that is equal to the integral of power dt. So work, knowing that power is dw dt, work is integral of power dt. All right, so what we're going to do is we're going to integrate this term. So Li di dt, that's your power, and then times dt. So what do you notice happens to dt? Well, it cancels. So U sub L is equal to the integral of Li di. Well, what are we integrating? Well, we're integrating the current in this case. The current goes from 0 to some value later on. So you end up with L, and then what's the integral of I di? Well, it's I squared over 2, and you evaluate that from 0 to I, and therefore the potential energy stored in an inductor is 1/2 Li squared. So that is the total potential energy stored in the magnetic field of the inductor at any given time, if you know the current at that moment. All right, I hope that video was helpful, and thank you very much.